So our next speaker is Desi Ivanova with Oxford University. She kindly agreed to give 2 talks at this workshop. One is this tutorial on experimental design, and then a research talk tomorrow morning. Yeah. First thing, exactly. The floor is yours.
All right. Yeah, so first of all, thank you for inviting me. I will be giving kind of an introductory tutorial on Bayesian experimental design. In just a brief show of hands, who has worked in Bayesian experimental design or like knows stuff about? Okay. So that might be a little bit too basic for some of you, but hopefully there is something for kind of everyone to kind of get some ideas and methods. Okay, so the tutorial will be mostly based on, I guess, my PhD thesis that I submitted last year, and also a review paper on what we call modern Bayesian experimental design that we published in Statistical Science also last year. And in terms of content, right, so I'll start with kind of the principles behind Bayesian experimental design, the information theoretic foundations of it. Which one is it? Yeah. And then we'll move on to computational methods. You know, how do we actually optimize these information-based objectives? I will talk about something that we call policy-based Bayesian experimental design. And I'll finish with some kind of future directions, open problems that, you know, some of you might be interested in. I would like to also caveat with the same sort of disclaimer as Jeremiah's, right? So this is very much based on my own work, and I may miss some of your work, right? So this wasn't on purpose, right? It's mostly, again, because of, you know, the kind of the subfield that I've worked on. I did try to kind of give references to other works as well, but kind of for more extensive references, please have a look at the review paper. Okay, so in the first tutorial, we sort of started with the assumption that we have data, right? So the data is given to us either by the universe or by some, you know, natural process. And based on that data, we're able to, you know, prove or disprove hypotheses, do some modeling and predictions, and also sort of make decisions. But very often, the data doesn't come to us via some, I don't know, supernatural phenomena. We can actually design our data collection process and run experiments to collect kind of more meaningful data for the tasks that we actually then care about. And just a very brief historical note, this is sort of the lady tasting tea experiment, which was sort of the first optimal experimental design of experiments that Ronald Fisher did to sort of answer the question, can a tea taster tell whether the tea or the milk was added to the cup first, right? So hopefully you kind of know of that experiment. I'm not going to go through that. So very brief history of optimal experimental design. So as I mentioned, Sir Ronald Fisher introduced and formalized this sort of optimal design of experiments in his seminal books, The Arrangement of Field Experiments and the Design of Experiments in sort of the late 20s and early 30s. But actually there is a Danish statistician, a lady called Kirsten Smith, that kind of the field of optimal experimental design is attributed to. So a few years earlier, she published in her doctoral thesis sort of this G-optimal design for polynomial linear models. And sort of in what followed in the next few years, people developed various what we call alphabetic criteria for designing experiments that were mostly based on the Fisher information matrix. A little bit later, when Shannon developed information theory in 48, Dennis Lindley introduced the information theoretic approach to designing optimal experiments, and a little bit later after that also generalized that to any sort of utility function, so going beyond information theoretic criteria and kind of taking into account decisions and downstream tasks. In kind of the 2000s in 2010s, when you know, computers became more powerful, we entered this era that I'm calling kind of the simulation era for experimental design, and basically that enabled us to design optimal experiments for many model-specific cases, right? So given a model, there were many model-specific methods that kind of worked really well. Some examples include mixed effects models, you know, various models in epidemiology, things like dose finding, and so on. And since the 2000s, we've kind of entered this era, or about the 2000s, 2020s, we've entered this era of the deep learning wave, right? Where variational methods and various neural-based methods now allow us to really scale these approaches to very high-dimensional problems, and also build methods that are completely model agnostic. And what we will be focusing in this tutorial is precisely this sort of later stage, right? So deep learning-based methods and variational approaches. Okay. Now, before we move on, I just want to highlight that, you know, experimental design is something that is quite widespread, right? So many sort of fundamental problems can be cast as an optimal design of experiment problem. It goes beyond the kind of the lady tasting tea experiment. So just a couple of examples. You know, if you're running an online survey, you may want to ask what is the next best question to ask to a participant. If you're in drug discovery, you know, what is sort of the most promising compound to try. And even things like active learning, right? So when you're building predictive models, you know, what data points should you label next? And throughout this tutorial, I will use this as a running example, right? So I want you to have a concrete example in your head, so that when we go through the methods, you can refer to the super simple case and see how things apply. So the example is super simple, right? We have, imagine you're a psychologist and you're trying to determine the subjective time value of money preferences of different individuals, right? And normally what people do is they ask questions of this form. Do you prefer some money now or some money later? Okay? And one possible design is to ask, do you prefer £150 now or £100 in 1 year? And another possible design is, do you prefer £50 now versus £100 in 1 year? And clearly some of these designs are better than others, right? So nobody will pick less money later, right? Regardless of who you ask. If you were to ask the second question, you may get some discrepancy between, you know, a graduate student who may prefer less money now and a professor who may be willing to wait for a year and get the bigger sum. And now, of course, we can parameterize this question, let's say by the reward that the participant is getting now and the delay, let's say in days, and we basically end up with an infinite number of possible questions to ask, right? So what we want to answer now is, what is a good way of ranking such designs? And we will be taking an information theoretic approach. So at a very high level, what we want to do in this optimal design procedure is to choose the design's psi so that the data that we collect after performing the experiment, will be denoting the data by y. This data is maximally informative about the underlying quantity of interest. Going back to our example, our quantity of interest will be the subjective time value of money parameter, right? And what we're going to do is actually describe the relationship between designs, parameters, and outcomes in a Bayesian probabilistic model. And specifically, we're going to assume that the model factorizes as a prior over the latent over the parameters and an observation likelihood, right? So the probability of the likelihood of the outcome given the unknown parameters and the designs. On the learning aspect of things, what we will be doing, right, is essentially parameter learning in this Bayesian model. And we have the standard Bayes rule. We have that the posterior is proportional to the prior times the likelihood. And I just want to highlight that this sort of parameter learning problem is very often referred to as many different things. System identification is one example, inverse problem, model calibration, and so on. Okay, so this is like, roughly speaking, the same problem. Right. So what are the designs and the outcomes and the parameters in our running example model, right? So our design will be the tuple of the reward now and the delay in days. The outcome is a binary, whether the participant accepts or rejects the delay. And theta is the model parameter in a model that we have in closed form, right? So the model comes from kind of this behavioral economics / psychology. Kind of experts in that domain has developed it. It's called a hyperbolic temporal discounting model, and this is the model that we are working with. We are assigning some prior, and that sort of defines our generative model for this experiment. Now, what do we mean by maximally informative? What will be the maximally informative design? And I hope a little graphic will help you sort of understand what we mean here. So, we start with some prior over our parameter, right? And our prior has some level of uncertainty. Once we select our design, so let's say we run an experiment with design Xi1 and observe data Y1, we end up with a posterior that looks like this, right? If we were to choose a slightly different design and obtain a different outcome, our posterior may look like this. And what we can see is that the uncertainty about the parameter theta in this case has barely moved, has barely changed from our prior uncertainty. And in this case, we have managed to reduce uncertainty about the parameter quite substantially. So this will be a better design than this. In the metric that we use to sort of quantify this reduction in uncertainty is the information gain, right? So the information gain will be defined as the entropy of our prior, and we're going to subtract the entropy of our posterior and end up, with this information gain metric. Now, in order to make this into a ranking criteria, before we actually observe our data Y, we simply take the expectation with respect to the sort of the marginal distribution of the outcome, and this gives us the expected information gain objective. Okay, and this is precisely what Lindley did in 56. I'll just pause for a second and see if everything is clear or if there are any questions. I see some notes, so I'll move on. Great. Okay. Now, we can write the expected information gain in a few different ways. So, first of all, the EIG is exactly equivalent to the mutual information between our parameters and our outcomes, conditional on the design. It is also equivalent to an expected utility with the KL divergence as a utility function, right? And it is also equivalent to this bold score that people use in active learning, the Bayesian active learning by disagreement score. And all of this is just doing a little bit of KL and Bayes rule gymnastics. But regardless of all of the gymnastics that you do, you always end up with something that is a doubly intractable quantity, right? And so what do we mean by that? We have an expectation, and inside the expectation we have quantities that are also intractable, right? So for instance, if we pick the posterior over prior formulation, the posterior is typically intractable, right, for general classes of models. If you were to pick the likelihood over the marginal formulation, the likelihood may or may not be tractable, and the marginal is also typically intractable. So, as a result, this EIG objective is very nice mathematically, but it is quite difficult to work with computationally, right? It is very hard to estimate, and it is even harder to optimize because of this nesting of expectations. And how this sort of estimation was done historically before the deep learning sort of era, and still to today, is to use a nesting of Monte Carlo estimators, right? And as a quick example, I'm using this likelihood to marginal formulation. This is a simple Monte Carlo estimator of the outer expectation. If we assume that the likelihood is analytic and that we can evaluate it, we can also form a simple Monte Carlo estimator of the inner expectation of the marginal here, and end up with an estimator that looks like this, right? So we have a nesting of estimators, or also called double loop Monte Carlo. There are various other ways in which you can do it using sampling. You can combine nested Monte Carlo with importance sampling. You can do Monte Carlo with a plus approximation. So if you were to pick the posterior of a prior formulation, you can approximate the posterior with Laplace, and this has been done in various works in the past. When it comes to optimizing the EIG, right? So let's assume that we can estimate it somehow using nested Monte Carlo or any other of these methods. What then happens is, generally people look at what the design space is, and if it is a small enough discrete space so that you can enumerate all possible designs, you would estimate the EIG for each of these candidate designs and pick the argmax, right? As long as there aren't too many of them. If your design space was continuous, then people normally use something like Bayes op to search over the designs, which is, as we know, computationally costly and doesn't scale very well to high dimensions. And there's some key issues with this two-stage approach, this estimation followed by optimization. First of all, it's very inefficient, right? So there is no computation that is shared between designs, and you would expect that if you have estimated the sort of the EIG of one design and you're just estimating the EIG of that design plus epsilon, it should behave relatively nicely. So there is no sharing of sort of this computation in this two-stage procedure. It is quite wasteful, right? So you may spend a lot of computational resources on really unpromising designs, and it scales poorly with the design dimension. So we're going to kind of look at a solution to these problems in what we're calling variational Bayesian experimental design. So let's go back to this double intractability, right? So if we were to pick, let's say, this formulation here, what we can do is actually use optimization, so some of these techniques that Jeremiah's discussed in the previous talk, and estimate or approximate some of these unknown densities. The key requirement for this will be to be able to sample from the joint, that is from kind of the model that we started with. And as a concrete example, we can take the nested Monte Carlo estimator that we just discussed, right? So as we said, this guy here in the denominator is intractable, and each of the instances will be different. And the convergence of this estimator is actually pretty poor, right? So the convergence rate is t to the minus 1/3 compared to order of t, square root t, sorry, for standard Monte Carlo estimators. It is also biased, right? So we have this log inside of the expectation, but it is asymptotically consistent, right? So as we sample infinitely many samples, we will converge to the correct thing. Now, what we can do, instead of sort of estimating the marginal distribution every time, is actually learn a functional approximator to this marginal, right? So we're going to have a parameterized function Q that we can actually plug in the denominator and evaluate and actually get an estimate of the marginal immediately without resampling. Now the cool thing is that when Q is a valid normalized density, we end up with a variational upper bound on the expected information gain. And we know that it is tight if and only if you are recovering the true marginal distribution. Now this of course will give us convergence rate of, what the standard Monte Carlo rate of convergence is, 1 over square root t, but it can be biased, right? So if your parameterized family does not contain the true marginal distribution, you will converge to something that actually is wrong. However, there is, something that we can do about that, or something that will allow us to at least quantify the level of that bias, right? So we can very easily get what we call sandwich bounds on the expected information gain, right? So what I just described here gives us a variational upper bound on the EIG. We can get a variational lower bound on the EIG as well, and actually, see what the spread between the two things is, and therefore kind of get a sense of how bad the bias might be. Now, we can estimate our expected information gain relatively efficiently. We can also sort of to a degree quantify the bias if a bias exists in these estimators. But remember that we still want to maximize the expected information gain, right? So how are we going to do that? The key idea here is to actually simultaneously estimate and optimize the expected information gain with stochastic gradients, right? So this was kind of an idea that that was published in 2020, both for likelihood-based and likelihood-free models, and nowadays it's very simple, right? Nowadays, we do stochastic gradient schemes for virtually everything, and the key here is exactly the same, right? So we're going to have our lower bound objective. We're going to view it as a function of our design and the parameters of our variational family, and then basically do a stochastic gradient scheme on that loss or on that objective function, right? So this sort of provides us a unified objective that allows us to both estimate and optimize it at the same time. And really what this gives us in terms of efficiency is that we're not going to be wasting computational resources on very unpromising designs, right? Because we'll be moving towards the optimum and we'll be tightening the bound as we optimize. Right. So I guess after the 2020s, we have this, better view of how we can optimize experiments with sort of continuous designs in continuous design spaces. And back to our example, what we end up having is an objective that allows us to quickly and efficiently come up with our first design. Okay. Now, of course, very often we actually want to run multiple experiments. And there are kind of two ways in which we can think about conducting multiple experiments. The first one is kind of this non-adaptive design idea, i.e. we will, before we run any experiment, we're going to decide on all of the T experiments that we want to run, and then run all of them in parallel or in batch, right? So I'm referring to this as non-adaptive design, but you may see it as static, batch, or open loop design as well. On the other hand, we have adaptive design, in which case you kind of want to design an experiment, observe an outcome, and then do some updating, and then kind of take into account the information that you learned from the design and the outcome when you are designing the next experiment. Now, the reason why I have a tick here is that actually what we just described is pretty much automatically extends to the batch design setting, right? So we can run variational Bayesian experimental design to learn a batch of designs rather than a single one. And this is kind of our simplified example. Our design, rather than one item of 2 dimensions, right, is going to be a batch of 4 2-dimensional objects, and we're going to learn this 8-dimensional design at the same time with variational approaches, for example. Now, obviously, this doesn't take participants' answers into account, right, and therefore will be inefficient, right? We're not assimilating the information that we are obtaining from participants in designing the next question. So the traditional way of designing experiments is, again, this 2-stage procedure, right? So we designed our first experiment, we ran the experiment and observed an outcome. What we are then going to do is perform a posterior update, and then we're going to use this posterior as our prior in the expected information gain objective to then design the next experiment. Okay? So we have these 2 stages, right? Posterior update and EIG optimization. And both of these steps are quite expensive, right? If you are running such an experiment with real human participants, it will be a little bit unfortunate if you tell them to sort of wait for 5 minutes until your MCMC has converged and you have re-optimized your expected information gain. So what can we do about this? Can we perform experiments quickly enough to be, applicable in sort of real-world adaptive situations? Right, so just highlighting some of the key issues with this traditional adaptive approach that I just described. So it is slow, right? What happened? Oh, okay. It is slow because of this posterior update and the optimization of the EIG. And it's also myopic, right? We're only optimizing for the next best design. We're not taking into account the entire sequence of T experiments. We're not planning ahead. So can we deal with these 2 items? And this is where sort of this, what we call policy-based Bayesian experimental design approach comes in. And the key idea is the following. Rather than spending all of these computational resources during the live experiment, we're going to take our model and we're going to train a policy. The policy is just going to be a function, right? We're going to learn a function that we can then deploy during the live experiment. And that function will give us optimal designs and take into account observations and sort of do the updating automatically, right? The key idea is that this will be happening offline. So we're going to move the computational burden from the live experiment into an offline pre-training stage. Okay, so the policy, as I said, is just a function that will be taking past data as input and will be outputting the next design. And just to highlight the traditional approach that I just described, right, this 2-stage procedure, is actually a special case of this policy-based approach, right? The traditional way of doing of experimental design is this expensive implicit policy, where stage number 1 is do a posterior estimation, and stage number 2 is maximize the EIG, right? Now, what we're going to do instead is introduce an explicit policy that we're going to parameterize with a neural network, right? That will, take our past data and output the next design. Okay? Any questions so far? Okay. So, what is this design network, right? So the idea is that this design network should be able to amortize or emulate the slow adaptive experimental design process, this slow implicit policy. Or in other words, the policy should be maximizing the expected sum of these expected information gains, right? So at each step of the experiment, we're gaining a little bit of EIG, a little bit of expected information gain. Once we sum it and take an expectation of the randomness in our data, this is the objective that our network should be optimizing. And this is a result that is pretty obvious to anyone that, I guess, has worked with mutual information before, right? This is saying that this sum of incremental EIGs is exactly equal to the expected information gain from the initial prior to the final posterior, right? This is all this is saying. And this was done in our ICML paper in 2021, and also by the group in Michigan of Xinhuan, almost concurrently. And here is the formal definition of it, right? So we have what we call the total expected information gain will be defined as this expectation under our model of the log of the likelihood of our history divided by the marginal of our experimental design history. Okay, and as we saw, this generalizes the traditional BED approach, and it actually provides an end-to-end objective. The reason why we like this is because we can actually approximate this expectation with samples from our model, and then inside of the expectation, we can actually use any of the variational approaches that we described in the previous section, right? So, as I said, yeah, the objective is still intractable, but what we'll be doing is, yeah, applying any of the approaches described before, just for the purposes of, I guess, completeness. In the original DAD, we're calling it DAD, I should have said that. So DAD stands for Deep Adaptive Design. In the original DAD approach, we are optimizing a tractable lower bound using, assuming analytic likelihood. And in a follow-up work that we call IDAD, or implicit deep adaptive design, we're sort of optimizing a tractable lower bound using samples only, i.e. extending that to implicit models as well. Is that okay? Great. So just a very quick note on what the IDAD objective is, right? So for for the optimization of the EIG based on samples only, right? So we're only relying on samples from our simulator. We're sort of taking inspiration from the representation learning literature, and specifically the info NCE lower bound on the mutual information from this paper in 2018, Vandenord, and the NWJ bound, which is actually a bound on the KL divergence. It's not a bound on mutual information, so it is, slightly more general. And with these bounds, what we're actually introducing is another small neural network, right? This small neural network is called a critic network, and this critic will be taking as inputs design outcome histories and parameter values, and will be outputting a real number, okay? So you can think about the critic network as an object that aims to approximate the density ratio of the likelihood to the marginal or the posterior to the prior. The two things are obviously equal, right? So we're going to have a critic network, and we're going to have a policy network, and we're going to be optimizing these two objects jointly in a single stochastic gradient scheme. In the next slide, it's not very important, right? So it's just here for completeness. These are kind of all the bounds that that we're using in this deep adaptive design framework. And the first one only applies to likelihood-based models, and the other two also apply to likelihood-free models. The key is, as I said, the form isn't super important. These are things that you can evaluate and you can, run stochastic gradient schemes on. The key point is that we're able to get unbiased estimates. In other words, we are able to run stochastic gradient schemes on with respect to both the policy and the critic, which then allows us to, train this policy network in an end-to-end manner with stochastic gradients, and it's applicable to both likelihood-based and likelihood-free models. Okay, so back to our running example. We have, right, do you prefer some money now or some money in the future? And now we have trained a little deep adaptive design network that sort of does the, takes the past data as an input and immediately outputs the next design, right? So, and this is how it goes. You start with 49 today versus $100 in 3 months. Human participant prefers the money now. Then the network adapts and kind of reduces the amount of the delay by, I guess, a third from 3 months to 1 month. The human participant still prefers sort of the money now. Then that's again gets adapted and the reward is offered even sooner. And then you can continue to do that and really tailor your questions to the participant that you are engaging with. Okay. Here is a quick overview of what some quantitative results actually look like. The first row is a heuristic approach from kind of a psychology paper. So they have developed almost like a tree-based algorithm for deciding on what the optimal questions are. And they're fixed, right? And that gives you mutual information of between 3.5 and 3.51. Right? So this is what I described as you can actually get a sense of how biased your estimates are by looking at lower bounds and upper bounds. So these are pretty tight bounds. So the heuristic approach gives us a mutual information of about 3.5 nats. A traditional, this slow adaptive experimentation that I described earlier, where after each experiment you're fitting a posterior and then optimizing the expected information gain. This is a method that was developed specifically for that model, right? So you cannot apply the same method to any other model. That gives you a mutual information of around 4.5, right? So between 445 and 454. And sort of this policy-based approach actually performs better than the traditional approach, right? And if you remember, the reasons why we, or if you remember some of the issues that we described with the traditional approach, one of them was the fact that we are doing greedy optimization, right? You are optimizing designs myopically. And this is one of the reasons why you're actually seeing better results with something that is approximate, i.e. it's amortized, compared to something that is much more computationally costly, as you can also see from kind of the deployment time, but it's only optimizing greedily. Right. So I mentioned the non-myopic aspect of it. Another reason why we might be getting better results actually is the fact that we're avoiding Bayesian inference. Okay, running Bayesian inference can be difficult to debug, right? Especially if you're running experiments in a sequence. Normally you may not have time to make sure that your MCMC has converged and do all of the diagnostic checks and so on. And so actually by avoiding some of these Bayesian inference, you might be limiting the error that gets propagated through the sequence of experiments, right? And another hypothesis is that learning to map past data to future designs might be just an easier task compared to doing the two-stage procedure. Okay, here is another quick experiment. That's kind of a, you're trying to locate these two hidden sources, and this is a deep adaptive design network that was again trained on data from that model. And as you can see, it's kind of exploring the space in this spiral. And once it finds a source, it sort of, stays there a little bit to make sure that it's got the correct place, and then continues. And similarly, we're seeing kind of better performance compared to traditional approaches, really much faster, right? And again, to highlight, that is really due to the fact that we're not doing posterior estimation, and we are kind of planning ahead, right? We're learning this non-myopic policy. Are there any questions so far? Yes, please.
Maybe it's a little like add to the end-to-end comparison to incremental.
This one?
No, a little bit behind, but no, wait, like 10 slides before. Like 10 slides before.
Oh, 10 slides before.
Sorry.
Just tell me. Oh, more?
Here. Here.
This one?
We should say total expected information gain because it's easier to train your policy in a way.
Say that again, sorry?
You're using the total EHE because it's easier in some way.
Yes.
But if you were to optimize this objective function,
This one?
yes, adaptively in a way, or doing bootstrapping, something like that. Well, you're posing that this is easier because you have all the experiments, right? And you're optimizing like one of the one.
Yeah. So this guy here contains T doubly intractable quantities, right? So each of these T doubly intractable quantities would require a lot of computation to estimate, yeah? And this one is a single doubly intractable quantity.
But
So
in the long run, if you have to estimate that expectation value,
yeah,
and if you have many experiments,
right. You mean large T?
like a large T.
Yeah.
Not a large T, but a large number for the Monte Carlo to estimate the expectation value.
Right.
And you have like another strategy to optimize this faster in a way with the using the incremental approach.
Mm-hmm.
This is valid still. I don't know if I'm posing my question well, but what I'm saying is total expected information gain is fairly better to compare to the incremental one. If you're doing this using a Monte Carlo for this.
Right.
But if you're doing something like bootstrapping, maybe you approach like you might achieve like a.
I think still the issue is like regardless of what whether you're doing Monte Carlo or something else, you still need to get a posterior, right? You still yeah.
And you're avoiding like trying to get like all the estimates of the posterior amplitudes.
Yeah.
Then maybe I can ask you.
Okay, we can check. Yeah, oh fine. Okay, so where were we at? Okay, so we are again performing better than the traditional approach, which is very, very slow in this case, and it does really, really badly actually. And in this case, actually, the reason for the very poor performance, to a degree, is the fact that we were a bit lazy with the variational posterior that we were doing here, right? We just did mean field Gaussian. And in this experiment, actually, the posteriors are really, really not Gaussian at all. At least not until you get large number of experiments so that your posterior actually collapses. Okay. Right, more recent developments. So, I talked about kind of the variational approaches that sort of kicked off in the 2020s. Then we moved to this policy-based approach that was developed shortly after. And I think nowadays people are really building on top of this policy-based approach quite a lot. I did not sort of go through an extensive literature review for that, but there are a bunch of presentations during the week to actually that actually goes into some of these more advanced methods. So there's presentations from Sakel and Dowlang and Jacopo and Nikolai, I guess others as well. That will be kind of going into these more recent advances. So what are these some more recent developments? I guess number one, we have seen a lot of development in the way that we're actually approximating these posteriors and the way that we're actually approximating densities. There is, quite a, I guess, substantial overlap with the simulation-based inference literature in the SBI community, right? So using things like conditional normalizing flows to approximate posteriors, flow matching consistency models, diffusion models, and so on, right? So these really, have some universal approximation properties that, you shouldn't be super worried about. Are you biased or unbiased, right? We are getting some really good approximation schemes that, at least in kind of the small dimensional problems that we're looking at, work really well. Then there is a bunch of developments in the policy parameterization and the policy learning, so kind of moving more towards the reinforcement learning literature, which is all about learning policies and optimal decision making. So we've seen some work that use transformer-based architectures to parameterize the design policies, also conditional neural processes, and so on, right? So this just lets you learn much more complicated and flexible design policies in this case. And of course, you can also substitute the policy learning approach itself, right? So some work have looked at soft actor critic algorithms. Obviously you can apply your favorite policy learning algorithm from reinforcement learning, PPO, and the other acronyms, T3 something something. So all of them should be in theory applicable. In the kind of the third direction of work, and it is something that I'll be talking about tomorrow a little bit, is going beyond parameter learning, right? So in this presentation, we solely focused on designing experiments for the purpose of reducing uncertainty in your model parameters. But oftentimes, maybe you work with a model that parameters have actually no meaning in the real world, and you actually don't care about the parameters. What you care about is making predictions, and you have a decision-making process that you actually want to optimize for. So you can think about this downstream decision-making. Another, in my opinion, quite cool area is active causal discovery, right? So rather than just focusing on parameters, you also have a graph that is parameterized in some way, and you're learning the causal structure as well as the parameters in the structural causal model. I'm sure there is more probably, but these are sort of the three main ones that I think the field has started working quite a lot towards. Right, and I just want to finish with kind of a brief section on limitations and future directions, and I would really like to hear what you think, because many of you have actually worked in BED, so let's see. I hope this is not too controversial. So number one, that shouldn't be controversial actually. So we have model misspecification, and in this case, I really mean you have a mechanistic model, you have a mechanistic physical model. These are the types of models that we work with in Bayesian experimental design. So I'm not dealing with neural networks and parameters that have no meaning and are basically non-identifiable, right? So we assume we have an identifiable model, and your parameters have meaning, and you want to learn those parameters. Now, because experimental design relies on the model twice, right? So you rely on the model to select your data, and you rely on the same model to fit that data, okay? And there are cases in which you actually end up with something that goes terribly, terribly wrong. And the simplest case is a basic linear model, right? So if you have a linear model, you're assuming you have a linear model, and the optimal design for linear models is to sample at the endpoints, right? So if your designs can go between -1 and 1, the optimal thing you can do is design here and nowhere else, okay? Now, if it happens that your model is actually not linear, there is no way to even detect that this model is non-linear, right? So the true data generating process in this picture is denoted by this dashed green line, curve, sorry. And the fitted, its maximum a posteriori fit is this blue line, right? So if you were being Bayesian and optimal, you sample here and you sample here, and this is your fit. If you were just doing random designs, right, sampling randomly from your design space between -1 and 1, you end up with a fit that looks like this, right? It's still not a good representation of the true data generating process, but it is much closer, and you can actually see, or like, you can actually detect potentially that there is something wrong with your linearity assumption, okay? So this happens in this super simple case. You know, now imagine you have a very complicated model with a very complicated design space, and you know, there is basically many things that can go wrong, and you may not be able to tell. Okay, so this is, I guess, future direction number 1. I think we kind of really need to think more deeply about how we design experiments, knowing that the models are unspecified, because they are. I mean, they always are, right? In the next future direction, which is, I guess, a little bit more contentious, is I feel like there's a bit of a methods application gap in the Bayesian experimental design community, or at least the Bayesian experimental design community in machine learning. So maybe that is a much smaller community. So, you know, we are developing these ever increasing in complexity methods, but I personally haven't really seen any sort of real world applications, right? And part of the reasons, I mean, I've listed some of the reasons here, and I'm happy to hear your thoughts. You know, number 1 is, you know, working with applied scientists is super hard. You know, it takes much longer to publish your NeurIPS papers. You know, we don't really have robust and scalable tools that, you know, a practitioner can just use out of the box. Something like, you know, PyTorch for deep learning or BowTorch for BaseOpt. We are relying on high fidelity good simulators, which are super hard and costly to develop. You know, obviously, I kind of mentioned that already, but misspecification, and then when you move to policies, sort of reward hacking is a big worry, right, for applied people. You know, if you're if you're doing clinical trials, you definitely don't want to be running the risk of your policies doing something strange and giving you super biased results. And finally, I feel like there's actually need to sit down and think about how we actually evaluate the benefit of doing active data acquisition, right? Being Bayesian optimal in a sense, right? So we look at mutual information, but there's so many things that kind of we need to care about, right? Is design diversity, it is, you know, robustness and specification, various other forms of robustness, you know, some of which Jeremiah has described earlier. And I'm actually quite happy that there is an applied talk that we'll hear on Friday from Dasha for Bayesian experimental design for reaction kinetics. So I'm really looking forward to that. Hopefully, yeah, some of my worries would be not such big worries. I don't know. So yeah, let me know what you think. And that's it actually. So here are some references. And yeah, I'm happy to take any questions.
Thanks. It was really to learn within this topic. Can you speak up, please?
Oh, yeah, sorry. It's thanks for the nice talk. It's a very interesting topic, I think, and I like how you laid out like all the future directions. I had a relatively narrow question about when you were in the slide of evaluation, quantitative results, and then that method is incredibly faster than the alternative. Is it obvious that like higher kind of EIG in that context is always better? Because as I understood, there are these several different bounds that you show in stronger, like higher bias and lower variance and the different trade-offs. And I guess obviously at the end you're able to estimate the EIG, not to evaluate the true value. So
So I think it's a very valid question. In the slides with the results, actually we're using the likelihood. So we're in the well-specified case, first of all, right? So if you're misspecified, that it doesn't make sense. But we're in the well-specified case, and we actually have access to the likelihood, meaning that we are actually converging to the true EIG. And in this case, higher means better. Yes. If we were using likelihood-free bounds, then the question is how tight are you is a big one, and we don't have an answer to that, right? So if you're in a likelihood-free case and you've estimated the EIG for two different methods, but maybe for one of them your bound is much looser than the other, then you can't really compare them. You can't really compare them like for like. Did that answer your question?
Yeah, thanks.
Okay, here and then down. Yes.
So in terms of deployment time, DAD or policy-based study is faster, obviously. But have you compared the accuracy, let's say, the DAD versus the real static batch design? Because you said, let's say, sequential design normally is greedy. So it's very easily go to local optimal. But you said DAD can, let's say, elevate the myopic issue. But have you really compared with that?
So the accuracy, so I guess the accuracy metric in this case is the mutual information. The higher your mutual information, the better.
Yeah, that's. But have you tried, let's say, a toy example? You know the real model, then you can have the evaluation. You know what I mean? Like you said, how do we evaluate the benefits?
Right.
So imagine if you have a toy model, so you know how the data generate, so you can evaluate the accuracy. MSE or metrics.
Yeah, I guess you could also look at the posterior average or something and compare to the true one, right? So mean squared error between your estimated parameter and your true parameter. Have we done that? Not in this paper. We have in other papers. And to your other point, using a model where you can actually compute things, I guess in closed form, right? You could run that experiment, and I'm expecting the numbers will be kind of aligned, right? Yes.
Thanks very much, Desi. So I wanted to ask a question on the training of policy for the policy-based BD. So imagine if there's say in a clinical trial where you might have data from phase 2, and you might train something with that data that exists and uses it to inform the next stage. What if you don't have an existing data set? How does that model policy training work?
So we are relying on a simulator, right? So the policy, actually, in everything that I've described, we assume no data. There is no data, right? You start with a model. You start with a model that is a good representation of the phenomena that you're studying, and you're using that model, trajectories from that model to actually train the policy. Now, if you have actual data, what you could do is, I guess, maybe do some model calibration to begin with, like do some learning, assuming your model is correct, right? And then train a policy for your next iteration of the data collection process.
Okay, so the core idea is there. You want to start with this simulation process that's the best to your knowledge.
To your knowledge,
and then-
yes. Yeah. Yeah. And there was one, yeah.
Yeah, thanks for a really nice talk. I had a question relating to the variation approach. Obviously, it's very powerful, but it has certain drawbacks. The optimization can be difficult, like highly non-convex. It relies on kind of choosing a good parametric family, etc.
Yeah.
Is there any work which kind of relaxes the parametric assumption and kind of works directly on the space of measures? So there's kind of a parallel literature where you kind of consider the optimization problem directly on the space of probability measures, and you can kind of simulate a gradient flow on that space, as opposed to parameterizing the target.
Yeah.
Has there been any work on that in this?
I think so, right? I mean, I'm not. I think there is, yes, but I can't tell you the references. I mean, yeah.
I have a question that is rather practical, I think. So if now I want to optimize one parameter, which is the frequency of a smart survey that participants receive every day. So there is one kind of external factor will be how burdensome participants will feel.
Right.
And is that something you need to incorporate in your model?
Probably yes.
That, I mean, does that mean I need to have a quite accurate estimation of this burdensome?
Yeah, I would say, any sort of cost should be embedded in the objective, right? So it's the burden for the participant, it's the burden for the company that is actually administering the whole thing, right? It is, so all these costs should be somehow embedded in the model, ideally, or in the objective as some form of penalty.
But I think it is feasible to do that kind of optimization.
Yeah, I think so. There are works. I know, at least in the base of literature, there are various ways to impose some structure on top of the design. So for instance, you may want to have sparse designs for whatever reason, right? You don't want to change too many things at the same time. So you can have a sparseness constraint, or similarly some other constraints. I guess if you think about it deeply enough. Yeah.
Okay, any final question? If not, let's, there's one.
So I have a quick question about policy-based approach versus more traditional when you first run the inference. Have you ever observed cases when it might be actually more difficult to train the policy, because policy needs to work over all prior, right? Whereas when you run an inference, you can restrict yourself only to a very small part of uncertainty where you know that your data is coming from. Have you ever observed problems with amortization or stuff like this?
So, I mean, honestly, the answer is no, because we only work with super toy problems. And that's kind of back to this real world application point that I'm making, right? I mean, the models that we use for Neurop's papers are pretty simple. But I would imagine if you're working for, I don't know, some fusion reaction, I mean, people do design experiments for these things. I know Google DeepMind has a very big simulator for these fusion reactors. I am not an expert, but that is one application where they put a lot of energy and effort. And I would assume that actually amortizing there would be super costly, right? And probably yes, kind of the more traditional approach will likely work better because of the complexities of the model, and I guess the difficulty of parameterizing maybe a suitable policy for the problem and so on. So I hope that kind of gives you an indicative answer, but I think it's kind of unknown, right? And it depends on the application.
Okay, let's thank Desi for the great talk.